China built sports facilities so advanced, the world is shocked. You're about to structures that redefined what's physically possible in sports facility stadium construction. These aren't ordinary venues, they're engineering impossibilities made real. Self-cooling ice that breaks world records, transforming water cubes, steel nests that defy gravity, and roofs that open like flowers. Every single one pushed the absolute limits of architecture, engineering, and construction. And it starts with the most structurally complex stadium ever conceived. Beijing National Stadium, Bird's Nest. You're looking at 42,000 tons of twisted steel, the heaviest steel structure ever built for a stadium that appears completely random but is mathematically perfect. The Beijing National Stadium holds 91,000 people inside a lattice where no two beam connections are identical. Engineers rejected every conventional design and chose something impossible. An interwoven steel web with 24 primary trusses wrapping around each other in 3 dimensions. Every single intersection was calculated individually. Computer algorithms ran thousands of simulations to find the strongest arrangement, creating what looks like chaos, but is pure structural optimization. The beams don't stack, they weave, distributing loads through geometry instead of mass. Then came the crisis. Halfway through construction, the planned retractable roof was abandoned. Removing a major structural element should mean redesigning everything. But here's what shocked engineers worldwide. They didn't change a single beam. The lattice was already perfect. The 3-dimensional grid maintained complete integrity without the roof it was designed for. And the final challenge: earthquakes. The entire stadium rests on seismic isolation bearings that let 42,000 tons of steel slide independently during ground movement, holding 91,000 people inside a web that redefined structural engineering. But while the Bird's Nest mastered steel, the building right next to it conquered something even more unusual: geometry borrowed from soap bubbles. National Aquatic Center, Water Cube. The water cube is the largest membrane structure ever built, and it's based on soap foam geometry. 4,000 ETFE cushions cover 1.1 million square feet, creating a building that looks like bubbles but functions like a precision instrument. Each cushion harvests solar energy while providing insulation, turning the entire exterior into an energy-collecting skin. But here's the engineering miracle nobody saw coming. This swimming venue had to transform into a curling rink for the Winter Olympics. You can't just drain pools and lay ice. The entire internal structure needed redesigning. Engineers developed a complete pool-to-ice conversion system that transforms the facility in 60 days. Modular support systems install curling sheets directly over the pools, creating perfectly level ice surfaces where Olympic swimmers once raced. The cushions themselves are the real breakthrough. Each one is a triple-layer pneumatic pillow that inflates to exact pressure, creating a self-supporting structure with no internal framework. The pattern isn't random. It's derived from air-feeling geometry, the most efficient way to partition 3-dimensional space. Scientists discovered this foam structure solves problems that stumped mathematicians for centuries, and Chinese engineers turned it into a building. From bubbles that became ice, the next facility took flowing water and made it stand still in concrete. Ching Yuan Olympic Sports Center. 50,000 seats, wrapped in a continuous spiral ribbon that defies every convention of stadium design. The Yuan Olympic Sports Center doesn't have traditional entrances and exits. It has 5 miles of pedestrian walkways that wrap the entire building at multiple levels, creating a circulation system where bottlenecks are physically impossible. The challenge was making concrete flow like fabric. The ribbon facade appears lightweight, almost delicate, but its load-bearing structure and architectural statement simultaneously. Engineers used parametric modeling to calculate every curve, ensuring the spiral maintains structural integrity while appearing to float around the stadium bowl. But the real innovation is what you can't see. The walkway system eliminates the crushing crowd flows that plague conventional stadiums. Instead of funneling 50,000 people through fixed gates, the continuous spiral distributes movement across the entire perimeter. Spectators enter at ground level and follow the ribbon upward to their seats, with the structure itself guiding traffic flow through pure geometry. The mountainous setting added another layer of complexity. Foundation work required anchoring into sloped bedrock at varying depths, with each support point calculated independently to handle the ribbon's twisting loads. While Ching Yuan made concrete spiral, the next stadium made it bloom like a flower that opens to the sky. Hjo Olympic Stadium. 80,000 seats surrounded by 28 petals that open and close like a living flower. The Hjo Olympic Stadium features a retractable roof where each petal operates independently, transforming the entire structure in just 18 minutes using synchronized hydraulic systems. Here's the engineering problem. Each petal had to cantilever outward while supporting its own weight and the weight of every petal above it. Traditional retractable roofs use linear tracks, but this design required curved movement along complex paths. Engineers developed a radial hydraulic system where each petal slides on custom curved rails, with sensors ensuring perfect synchronization. If one petal falls behind by even inches, the entire system stops to prevent structural collision. The cantilevered sections extend over 90 feet without visible support columns, using a hidden ring truss system embedded in the stadium's upper bowl. Steel cables run through the compression ring, suspending each petal from above while allowing independent movement below. The result is a roof that appears to float while carrying thousands of tons of steel and weather protection. But the ultimate test came during construction, installing 28 moving sections that had to align perfectly when closed. Each petal was fabricated off-site, transported in pieces, then assembled in position, a three-dimensional puzzle, where every piece had to fit within millimeters. This stadium proved petals could move, but the next one proved they could support an entire upper bowl while appearing to touch nothing at all. Guangjo International Sports Center. 80,000 seats in an earthquake zone, with an upper bowl that extends 90 feet outward, with no visible support. The Guangzhou International Sports Center looks like a lotus flower, but that delicate appearance hides one of the most aggressive structural systems ever designed for a stadium. The challenge was eliminating columns. Traditional stadiums use hundreds of supports between upper and lower bowls, creating obstructed sightlines. Engineers designed a ring truss cable system that suspends the entire upper bowl from a massive compression ring at the roof level. Steel cables drop down from above, holding tens of thousands of tons of concrete and seating in midair. But here's where it gets impossible. This is an earthquake zone. The compression ring had to be flexible enough to absorb seismic movement, while rigid enough to hold the suspended bowl steady. Engineers used a hybrid system. The ring itself is segmented, with expansion joints that allow controlled movement during ground shaking, while the cables maintain constant tension through hydraulic dampers that adjust in real time. Construction required building the roof first, then hanging the upper bowl beneath it completely backwards from normal stadium construction. The compression ring was assembled at ground level, then jacked into position using synchronized hydraulic lifts at 48 points simultaneously. One miscalculation and the entire ring could twist, making cable installation impossible. The Lotus design saved thousands of tons of structural steel, but the next facility took that weight savings and invested it all in surviving something far more violent than earthquakes. Shenzhen Bay Sports Center. A spring-shaped tower rising from the bay, designed to survive typhoon winds exceeding 100 miles per hour. The Shenzhen Bay Sports Center sits on waterfront land where the real challenge wasn't the building itself, it was what lay 70 feet below. The bay soil is soft sediment that can't support conventional foundations. Engineers drove pile foundations through 70 feet of unstable ground until they hit bedrock, creating a forest of concrete columns beneath the structure. But piles alone weren't enough. The spring design meant asymmetric wind loads that could twist the building off its foundation during a typhoon. So they engineered a spiraling structural system where the exterior frame and interior core work together. Wind hits the curved exterior and gets distributed through interconnected steel members to the central core, which transfers loads down through the pile system. The spiral isn't decoration, it's a wind distribution network that turns devastating lateral forces into manageable vertical loads. The real test came during Typhoon Mangkhut. Sustained winds of 95 miles per hour with gusts exceeding 110 struck the building directly. The structure experienced zero damage, not a single facade panel cracked, not one interior space flooded. The spiraling frame flexed exactly as calculated, dissipating energy through controlled movement. While Shenzhen Bay conquered wind through spiraling steel, the next stadium eliminated wind problems entirely by making it flow straight through the building. Shenzhen Universiade Sports Center. 60,000 seats in subtropical heat with no air conditioning, yet internal temperatures drop 12 degrees below outside through pure engineering. The Shenzhen Universiade Sports Center is wrapped in 11,000 unique triangular panels that form a crystal-like exterior, and every single panel was designed to channel airflow. This is parametric design at its most extreme. Engineers used computational modeling to calculate wind patterns around and through the structure, then optimized each triangle's angle to maximize natural ventilation. No two panels are identical because each one responds to specific airflow conditions at its exact location on the building. But here's the real challenge. The panels had to provide ventilation while maintaining structural rigidity and weather protection. Each triangle is a composite sandwich, perforated aluminum exterior, insulation core, and structural backing, assembled in a pattern that creates thousands of air channels. Hot air rises through the lower panels, draws cooler air in from shaded sections, and exhausts through upper vents in a continuous thermal cycle. Construction meant fabricating 11,000 custom pieces off-site, each labeled with precise positioning coordinates. Installation teams used laser guidance systems to place panels within millimeters of their calculated positions. Any deviation would disrupt the airflow patterns and destroy the cooling effect. The result is a naturally ventilated stadium in one of China's hottest cities, proving mechanical systems aren't always the answer. But the next facility faced a threat where ventilation means nothing, the ground itself trying to tear the building apart. Chengdu Phoenix Hills Sports Park. 60,000 seats in Sichuan province, where earthquakes don't just shake buildings, they destroy them. The Chengdu Phoenix Hills Sports Park sits in one of China's most seismically active zones, wrapped in a facade that appears to ripple like fabric frozen mid-wave. Making concrete look soft was the architectural challenge. Making it survive earthquakes was the engineering nightmare. The solution is base isolation, on a scale rarely attempted. 620 isolators sit beneath the entire structure, allowing the stadium to shift 16 inches in any direction independent of ground movement. During an earthquake, the ground shakes violently while the building glides on these bearings, absorbing energy that would otherwise tear it apart. But here's the complexity. Base isolation works for rigid structures, not flowing organic shapes. The rippling facade meant asymmetric mass distribution, some sections heavier than others, creating uneven seismic forces. Engineers calculated the exact weight and balance point of every facade section, then positioned isolators to handle specific loads at specific locations. Each bearing is individually calibrated. The ones under heavier sections use stiffer springs. Lighter sections use softer ones. Construction required building the substructure first, installing all 620 isolators with millimeter precision, then constructing the entire stadium on top of this movable platform. One misaligned bearing, and the whole system fails during ground movement. While Chengdu built a stadium that moves with earthquakes, the next facility built a roof that moves for an entirely different reason, and it's the largest of its kind on Earth. Greater Bay Area Sports Center, Guangzhou, Nanchcha. 80,000 seats under the world's largest retractable stadium roof, 1.3 million square feet of lotus petals that open and close hydraulically. The Greater Bay Area Sports Center in Nanchcha sits on reclaimed land where nothing should be able to support a structure this massive, let alone one with a moving roof system carrying thousands of tons of steel. The foundation problem was immediate. Reclaimed land is essentially compressed fill that settles unpredictably. Engineers drove deep pile foundations through the reclaimed layers into stable soil below, creating a rigid platform. But here's the twist. The piles had to support not just static weight, but dynamic loads from the moving roof sections. Every time the roof opens or closes, weight distribution shifts across the entire structure. The lotus petal roof uses a radial hydraulic system with independent sections that fold outward from the center. Each petal rides on curved tracks with synchronized motors, 1.3 million square feet of roof transforms in 23 minutes. The hydraulic system monitors load constantly, adjusting pressure to prevent any single section from bearing too much weight during movement. But the real engineering challenge was tropical rainfall. The roof had to channel water even while moving, so engineers designed drainage channels that remain functional in every position, open, closed, or anywhere between. Water flows through calculated paths, regardless of roof configuration, preventing pooling that could add catastrophic weight mid-movement. While Nanchcha built the largest moving roof, the next facility built the fastest ice surface in history, where technology invisible to your eyes broke world records visible to everyone. National speed, skating oval, ice ribbon. 12,000 seats surrounding ice so fast that world records fell repeatedly during Beijing 2022. The National Speed Skating Oval, the ice ribbon, uses a carbon dioxide direct cooling system that controls ice temperature to within 0.5 degrees across the entire surface. This isn't just cold ice. This is precision-engineered ice, where molecular structure determines Olympic outcomes. Traditional ice rinks use indirect cooling refrigerant chills, a fluid that chills the ice, losing precision at every step. The ice ribbon pumps liquid carbon dioxide directly through pipes embedded in the concrete slab, giving engineers exact control over every square foot of the 400-meter track. Outer lanes can be 0.3 degrees colder than inner lanes to compensate for centrifugal force effects on skater speed. But controlling temperature meant nothing if the structure couldn't support it. 22 ribbon-like glass panels wrap the exterior, each one a structural element supporting the roof while allowing natural light. The panels aren't vertical, they curve and twist in 3 dimensions, requiring custom steel frameworks calculated individually. Installation meant lifting massive glass sections into position where tolerances measured in millimeters, because misalignment would concentrate stress and shatter the panels. The roof itself presented another problem, spanning the oval without internal columns while supporting snow loads in Beijing winters. Engineers used a cable net structure suspended from compression rings at the perimeter, creating a column-free interior that doesn't interfere with sight lines or air circulation patterns critical for maintaining ice quality. While the ice ribbon perfected ice through invisible technology, the next building made structure disappear through visible innovation, a gymnasium where the roof appears to float on nothing. Guangjo Nanchcha Gymnasium. 8,000 seats beneath a swooping roof that touches the ground at only 4 points. The Guangzhou Nanchcha Gymnasium uses a cable net structure to create column-free interior spans that seem to defy gravity because the roof isn't pushing down on supports, it's hanging from them. Here's how it works. 4 massive concrete pylons anchor the corners, and steel cables radiate outward from compression rings at the top. The entire roof hangs from this cable network like a tensioned fabric, but it's supporting thousands of tons of steel, insulation, and weather protection. The cables are constantly under tension, which means they're always trying to pull the pylons inward. Engineers had to calculate exact counterweights and foundation anchoring to prevent collapse. But the real challenge was typhoons. Guangzhou sits in a region where typhoon winds create massive uplift forces that try to rip roofs off buildings. With a cable net structure, uplift is actually advantageous. It increases cable tension, making the system stronger. But during installation, before all cables were connected, partial wind loads could catastrophically overload individual sections. Construction required assembling the cable network in a precise sequence. Install cables in the wrong order, and tension distribution fails. Some cables go slack, while others overload and snap. Engineers used computer simulations to determine exact installation steps, with tension monitoring at every stage. The roof was built from the center outward, with each new cable adding calculated load to the existing network. The result is a roof that appears weightless because it's designed around tension instead of compression. But the next facility didn't just float a roof, it floated an entire Olympic venue inside abandoned industrial ruins. Big Air Shougang. A ski jump rising from an abandoned steel mill, surrounded by massive industrial cooling towers that once powered Beijing's factories. Big Air Shougang is the world's first permanent big air facility, and engineers had to build it inside a brownfield site contaminated by decades of steel production. The foundation challenge was immediate. Soil testing revealed heavy metal contamination and unstable ground from years of industrial activity. Conventional remediation would mean excavating thousands of tons of toxic soil. Instead, engineers designed an elevated structure that minimizes ground contact. The jump ramp rises on steel columns that pierce through contaminated layers into stable ground below, leaving most of the polluted soil undisturbed. But here's where it gets complex. The jump structure had to integrate with preserved cooling towers that are now protected industrial heritage. The towers aren't just backdrop, they're part of the structural wind analysis. Engineers modeled airflow around the towers to ensure they don't create dangerous turbulence at the jump landing zone. Wind tunnel testing revealed the towers actually provide beneficial wind blocking during certain conditions. The ramp itself is a cantilever structure, extending 192 feet at a 41-degree angle. Skiers launch at 60 miles per hour off a surface that can't flex or vibrate. Any movement disrupts takeoff angle and creates catastrophic crashes. The solution is a triangulated steel framework with cross-bracing every 6 feet, creating rigidity through geometry rather than mass. While Big Air preserved industrial history, the next facility created architectural history through a roof structure so mathematically complex it required entirely new design software. Nanjing Olympic Sports Center. 61,000 seats beneath a pedal-shaped roof that spans without internal support columns, not through cables or trusses, but through parametric geometry that turned the roof itself into the structure. The Nanjing Olympic Sports Center integrates a stadium, aquatic center, and gymnasium into one cohesive complex, where the roof design dictated everything below it. Traditional roofs separate structure from skin beams, hold up cladding. This roof is both simultaneously. Engineers used parametric design software to generate a surface where curvature provides strength, eliminating the need for heavy steel frameworks underneath. The pedal shape isn't aesthetic choice, it's structural optimization. Computer algorithms tested thousands of curve variations to find the geometry that carries loads through form alone. But here's the construction nightmare: building a curved surface where every panel is unique. The roof required fabricating 7,000 individual panels, each one a different size and shape, numbered and positioned with millimeter accuracy. Assembly teams used total station surveying equipment that triangulated exact three-dimensional coordinates for every panel install. One piece wrong and the entire geometric structure loses integrity. The integration challenge was equally brutal. The stadium roof had to align with the aquatic center roof and the gymnasium roof, creating continuous flowing forms across 3 separate buildings. This meant coordinating foundation settlement across the entire site. If one building settles faster than the others, the roof connections tear apart. Nanjing proved roofs could be self-supporting through pure geometry. The next stadium adapted foundation technology to some of the softest soil in China. Sujo Olympic Sports Center. 45,000 seats, built on the Yangtze River Delta, where soil is so soft that buildings sink without warning. The Sujo Olympic Sports Center sits on ground that's essentially compressed mud. Engineers faced the nightmare scenario of constructing a massive stadium on a foundation that wants to swallow it. Traditional shallow foundations were impossible. The solution was a deep pile system, driven 200 feet through layers of soft clay, silt, and sand until reaching bedrock. But here's the complexity. You can't just drive piles randomly. The stadium's asymmetric design meant uneven weight distribution, with one side significantly heavier than the other. Engineers calculated load paths for every structural element, then positioned over 1,000 piles at precise locations to handle specific forces. Each pile is a reinforced concrete shaft, 2.5 feet in diameter, installed using rotary drilling that excavates soft soil before pouring concrete. But drilling through varying soil layers created another problem. Different layers settle at different rates. Some piles penetrate through 12 distinct geological strata, each one with different compression characteristics. The solution was differential settlement analysis. Engineers modeled how each pile would settle over time based on the soil layers it penetrates, then pre-compensated by building the stadium slightly uneven. Sections predicted to settle more were built higher initially. So as settlement occurs over decades, the stadium levels itself through calculated subsidence.